Basic vector operations. Adding vectors in the opposite order gives the same resultant. So if we add red to green, we get the purple vector. If we add green to red, the opposite order, we still get the same result. Even if the vectors are not at right angles, they can be added graphically by using the tail to tip method. The resultant is drawn from the tail of the first vector to the tip of the last vector. So here we're adding v1 to v2. So we draw v1, then we put v2 with its tail at the tip of the first, then we're adding v3. So we put the tail of v3 at the tip of v2. Finally, we start at the very beginning and we draw the resultant to the tip of the final vector. And the order in which you add them does not matter. So you can start with the green vector, then red, then blue, and you'll still get the same resultant vector, the same length pointing in the same direction. In order to subtract a vector, we add the negative of that vector. The negative of a vector is defined as the same vector but in the opposite direction. So if we take this red vector and we want to subtract the blue vector, that's the same thing as adding the blue vector, but we change the direction. So instead of the tip being down here, now it's up here. When we add those together using the tail to tip method, we end up with our resultant. A vector v can be multiplied by a scalar c. The result is a vector cv, which has the same direction as the original vector v. However, if c is negative, it will also change the direction of the vector. For example, if c is the number 2, then if we have 2v, that vector will be twice as long as the original vector. If c is negative 1/2, it will shorten the vector to half of its original length, and it will switch the direction since it's negative. Any vector can be described as the sum of two other vectors called components. These components are chosen perpendicular to each other and can be found using trigonometric functions. So for example, v can be broken down into its horizontal component and its vertical component. Those two components are perpendicular to each other. Here are our functions, our trigonometric functions. So if this is our angle theta, sine theta is going to be this side here, which has the same length as v sub y, right? We can take this vector, just put it over here, it has the same length and direction. So sine theta is vy over the hypotenuse v. Cosine theta is adjacent over hypotenuse, vx over v. Tan theta is opposite over adjacent, vy over vx. And Pythagorean theorem still applies. V squared, the hypotenuse squared, is equal to the x component squared plus the y component squared, since those are the legs of a right triangle. In order to remember the right triangle properties and to better identify the functions, it is often convenient to show these components in different arrangements. So for example, remember on the last slide I took vy, which was originally over here, and I just moved it over here. You're allowed to move a vector as long as you don't change its length or direction. Using the tip to tail method, we can sketch the resultant of any two vectors, but we cannot find the exact magnitude of the resultant v here, since v1 and v2 in this sketch are not accurate nor precise enough. However, we now know how to break v1 and v2 into components. See, v1 can be described as its x component plus its y component, and same with v2. And since the x and y components are one-dimensional, they can be added as such. So the x component of the first vector plus the x component of the second vector gives us the x component of our resultant, and same with the y components. Let's go through it step by step. Draw a diagram and add the vectors graphically. Choose x and y axes. Resolve each vector into x and y components. Calculate each component. If we know the length of the hypotenuse and we know this angle theta, then we can use trigonometry to calculate the length of the components for both triangles. Finally, add the components in each direction. So we add the x components together, and we get the x component of our resultant. Then we add the y components together and get the y component of our resultant. Now that we have the x and y component of the resultant, just draw the answer from the tail of one to the tip of the other. Graphically determine the resultant of the following three vector displacements: 24 meters 30 degrees north of east, 28 meters 37 degrees east of north, and 20 meters 50 degrees west of south. First, we choose our x and y axes, and we draw all of our vectors. In this case, we can draw them all from the origin if we would like. Next, find the x and y components of each vector. We're going to start with the first vector, d1, and here's our x component, here's our y component, so this is d1x, d1y. If this angle here is 30 degrees, then sine of that angle is going to be opposite over hypotenuse. So that would be the y component over the hypotenuse. Cosine 30 is going to be the x component adjacent over hypotenuse. So that's the x over the hypotenuse. So we can rearrange this to solve for the y component and the x component. See, if we multiply both sides here by d1, the hypotenuse, it cancels out, and we get d1y equals the hypotenuse, 24 meters, times sine 30. That gives us 12 meters for our y component. For our x component, we're going to multiply both sides by d1, cancels out over there. Therefore, the x component is going to be the hypotenuse times cosine 30, which is 20.7. Next, we'll do the same exact thing to the second vector. So the second vector is 28 meters long, so that's this one here. So this is d2. So we draw our x component and our y component. That angle is 37 degrees. We use our trigonometric functions to find the lengths of the legs. Finally, we do the same thing with the third vector. Now this one's a little different. These vectors are both going to come back negative because they're going south and west. And since north is positive and east is positive, that means that west is negative and south is negative. So these vectors are both pointing in the negative directions. All right, so we total up these values. Remember, for D3, both of those vectors were negative. They can be negative because, remember, they're in one dimension. When you have a one-dimension vector in either the x or the y dimension, you can use positive or negative to signify north or south or east or west. So we add up those values and we get the components of our resultant. We can then use the Pythagorean theorem. Since we know the length of both of the legs, we can find the length of the hypotenuse, which is the magnitude of our resultant vector. Finally, to find the direction of the resultant, we can use inverse tangent. Tan theta is opposite over adjacent. Since the opposite side is going to be the y component and the adjacent side is the x component, we see that we can then use inverse tan, and we get that our angle must be 43.8 degrees.